Because of this combination, I denied the Ashutosh.
Okay, Ashutosh is our next speaker, and he will be speaking on this recording of univariate multiplicity codes.
Hi everybody, thanks for staying till almost time up. I realize I'm the last person standing between you and the Marine Drive dinner.
That's great.
I should try not to spoil your appetite first. So I'll be talking about some work with Rohan Goyal, Prahlad and Mrinal. Prahlad and Mrinal are here. Rohan Goyal is going to join. Huh? So yeah, Rohan is also in the Zoom call. Hi Rohan. She's about to join MIT as a student. Yeah, some of the slides I did to Mrinal, by some I mean. Okay, good. So, okay, so we have, so Mrinal introduced codes and stuff a bit earlier. So, we have thought a little bit about constructing codes with certain property. Now we will think about sort of another, the other end of the problem. Which is now that the code has been constructed, how do you do decoding? And in particular, the first keyword in the title, which is list-decoding. But first we must see what it is. So, for our purposes, a code is a collection of strings. Spaced apart in Hamming distance. And why do we want this? We want this so that if there is some receiver, like that star over there, we want to be able to decode it, which is to say, find out a code word that is nearby. So therefore, it could have got a bit corrupted, but that maybe was the original code word. So just by the fact that every pair of code words is delta apart, if you draw a circle around the receive word of radius delta by 2, there should be at most one code word within that circle. This is just from it. So the unique decoding problem is just to find this. So within a circle of radius or a ball of radius delta by 2, find this code. But if you notice, if you make that circle a bit bigger, there might be maybe 4 code words in the list, which is still not too many. So the list decoding problem is even in a slightly larger radius, I'm sure that there will be. Rather, I tell you that there will be, but if it so happens that there are only a few code words in this slightly larger radius, find all of them. So this way we can handle a few more errors. So one thing is we want the list to still be polynomial size. If the list is super polynomial size, then we obviously can't do it in polynomial time. So we do need to know what is this largest possible radius for which this is even possible. Whereas the sort of theoretical upper bound on what this radius could be is called the capacity. The capacity is just 1 minus L. So rate is like, again, I'll show you later, but rate is sort of the density of information. So if we go beyond that, question doesn't really make sense. So our question is, if we can do unique decoding, how much bigger can we make this radius? Can we go all the way up to capacity, if that's possible? So again, we'll not talk a bit about resolvable code, but just to refresh your memory. This is a basic fact about polynomials. 2 distinct degree d polynomials evaluated on some set of size n can't agree on more than d points. Why is this? Because if p and q are these polynomials, then p minus q is also of degree d, at most d, and therefore it can't have more than d vanishing points. So therefore these have to disagree on a large number of points. So that is the motivation for read-solvable codes. What are the code words of read-solvable codes? Evaluations of polynomials of degree d on some set of some set. So the distance is, okay, I'm going to be a little sloppy with plus 1s and minus 1s throughout the stuff, but based on that, that's the distance. Hence the unique decoding radius is n minus d by 2, and that's the rate. Why is that the rate? Because degree d polynomial has d plus 1 coefficient, so that's sort of the density of information. And so the list decoding capacity will be 1 minus it. Okay. Oh, I have not divided by n. I'm supposed to divide by n. By the way, the degree factor is also true if you include multiplicities. What do I mean by that? When we were talking about the p minus q and that it can have at most d zeros, not just that, but if you were to count the number of derivatives up to which it is 0 at every point, the sum of those in total can be at most 1. In other words, to factorize the polynomial, the sum of the multiplicities of all the roots can be at most 2. So what this gives us is something called univariate multiplicity codes. So if along with evaluations of the polynomial, you also give evaluations of the derivative of the polynomial up to some order, then now the symbols are these blocks, and if you want to see where how many locations these blocks can agree on, it can be at most d by x. So the distance is n minus this. So this is just one extension of resolving codes. There are many others. There are obviously remember there are coded resolving and name drop some of these later. But univariate multiplicity codes, this is the code that we are going to try to list to decode today. So before we go to that, what is the read-Solomon list decoding problem? The received word is this, some alpha 1, beta 1, alpha 2, beta 2, some n collection of pairs. And purportedly, there is some p or many p for which, for many pairs, we'll quantify this later, p of alpha I is equal to beta I. And we want to find every such p. If you were to think of, if you forget all about codes and you just look at that problem, that is equivalent to noisy polynomial interpolation. So if you were to think about it that way, it's there. And for unique decoding, there are many algorithms going back many decades. So Wellecamp-Welch, Wellecamp-Macy, and so on. But what about going beyond unique decoding? Well, first, what do we know at all? So here's a statement due to Johnson. We call it the Johnson bound, or the radius, we call it the Johnson radius. So for read-Solomon codes, it says that the number of code words in the list is still polynomial when the number of agreements is root n, or say you go to a radius of n minus root n. So you can notice that that is smaller than the number of agreements for unique decoding. So it would be nice to have a list decoding algorithm that goes up to us, which we do, by the way. A similar statement for univariate multiplicity codes. If you noticed earlier, D became D by S, here also it's D by S. So, question, do we have decoding algorithms that go up to here? Yes, good news. Oh, it's a big radius, but it's not the first.
The first one is for any code, right? Not the.
Yeah. I've written ND, like D is the degree of.
Okay.
The general statement is 1 minus under root 1 minus 6. So here are a few influential list decoding algorithms. These are sort of in the line of work that I'll be talking about. I'll start with the very first one and keep improving it till our work. So for resolver codes, Sudan in 1995, that doesn't quite go up to the Johnson radius. Guruswami-Sudan does, few years later. And Aleknovich in 2002 improved the latter, Guruswami-Sudan, to nearly linear time. Beyond the Johnson radius, resolver codes are not super well understood yet. I'll say more about that at the end, I guess. But we don't know this. For univariate multiplicity codes, Nielsen gave an algorithm, again going up with the Johnson. So, but there are a couple of other variants of read-Solomon codes that can be decoded up to capacity, and we do have algorithms for this. The first is folded read-Solomon codes. That's all I'll be saying about it. But so are univariate multiplicity codes. The algorithm is due to Guruswami and Wang, and independent but spiritually similar one given by Kopparty. And not only that, so not only can you find a list of polynomial size, but there's a randomized algorithm to prune this list down to constants. Okay, so problem solved, right? Like what are we going to do? But the thing is, spoiler, what we will do is Guruswami and Wang's algorithm is efficient, but it's not nearly linear. So what we have done is improve it to nearly linear. How do we go about this? Let's start at the very beginning. The only algorithm I mentioned, which is before I was born, Sudan's algorithm. So what is, recalling again what read-Solomon list decoding is? You have some pairs, and you want to find every p for which p of alpha equals beta I for many i. So all the algorithms that I'll talk about today will have two big steps. The first step will be an interpolation. In this case, what Sudan thought of doing, and this is inspired by Wellecamp-Welch, but more generalizing. So first, find a non-zero bivariate polynomial cubes, which number one vanishes on all the input points. Number two does not have too large degree. So In some literature, you'll see this being called as an explanation polynomial. Find a bivariate polynomial that vanishes on all the input points. So, illustration there could be sort of those black points are the input points on some plane, and you find a bivariate polynomial that vanishes on all. And you wanted to have not too much. Now, here's a fact, and this is not too hard to do. In fact, it's very easy to do, which is that if some R of X agrees with the receiver on many points, so then you want it to be in your list, right? If R of X agrees with the receiver on many points, you want it to be in your list. R of X are rather evaluated of R of X. Then it so happens that Q of X comma R of X is identically equal to Q. And this can be easily seen by just computing Q of X comma R of X. You'll see that it has too large degree for it to not be. Therefore, what would the second step be? If everything in the list satisfies this, then the second step is just factorization. So find every R of X as y minus R of X divides Qx. Very simple, very nice algorithm. This many is not quite the Johnson radius, it's a little less, but very nice template of an algorithm that other people will subsequently improve. Not too much later, Guruswami and Sudan improved this the following way. So they wanted QXY to not just vanish at the input points, but vanish up to high multiplicity. And instead of having individual conditions on the degrees of X and Y, take the weighted degree of both of them and say that it has to be small. And with these little tweaks, this algorithm can actually decode all the way to the Johnson radius. This is an efficient algorithm, but not nearly linear time. The bottleneck is the interpolation step 1. Step 2, the factorization step. Many of our smartest minds have been working on factorization. So the bottleneck was the interpolation step. So Aleknovich, a few years later, provided a speed up of this interpolation. So if you recall, we wanted a cube of small degree that vanished on all of these input points. And what he observed was that the set of polynomials that vanished on this sort of input points is like a lattice. Why is it like a lattice? You can add them, you can scale them, they will still continue to vanish on these points. That's not going to change. So, and we wanted a small degree polynomial that vanishes on these. If you think of degree as your measurement norm, weighted degree, then the problem is equivalent to finding a small vector in this lattice. And he does give a lattice shortest vector algorithm. You can use a different one if you like. But this nice, cute observation by Aleknovich led to a speed up of the interpolation step. And he didn't change the factorization step because that was not. So what has happened so far? We have an algorithm to list decode Reed-Solomon codes up to the Johnson radius, and it runs in nearly linear. Now, can we make it run nearly linear time? Our question: can we do this for the other variants of Reed-Solomon codes? Because, like I said earlier, we know about the other variants that they can be decoded all the way up to capacity. So, can a similar speed up be done for them? But first, we have to see what univariate multiplicity codes are and what the decoding code. So the received word is of this form. So if you remember earlier, it was alpha 1, beta 1, alpha 2, beta 2, alpha and beta n. In this case, we are going to give some more information, which is supposed to be the derivative of the polynomial at both points. So up to order s. This is the received word for univariate. If you're curious, that whole thing is one block. So this the block length, if you know what that is not ns, it's length, but all of those things together, it's one symbol altogether. And the decoding problem, if Reed-Solomon decoding was noisy polynomial interpolation, then this univariate multiplicity decoding is noisy. So Guruswami and Wang gave list decoding algorithm for this, and luckily it's not too different from the ones we have seen. So the step 1 is again interpolation. So instead of a bivariate polynomial Q, this is going to be some m variate polynomial. M will be something at most s. And we are going to impose an additional constraint on what Q should look like. So Q has to look like this: A naught x plus A1x y1 plus A2x y2 and so on. Q must necessarily be of this form. And rather than a degree constraint and then inferring this nearby polynomial stuff from the degree constraint, we are just going to say this directly. If R of x is close to the received word, then Q of the must be identical. And the way they do this is they set up and solve a system of linear. So, I mean, if all of this seems a bit much, don't worry. I'm just saying that it follows the same template as Sudan's algorithm quite a while ago. Step 1, interpolation, and step 2, not quite factorization, because it's not Q of x Rx anymore. There's a bunch of more derivatives. So now you need to solve a differential equation. The form of the differential equation is already given. So it's basically a differential equation of that form. Since we know we are forcing Q to be a certain way, what we need to do is solve a differential. So this is efficient and it decodes up to capacity or arbitrary. But it's not nearly linear time. Our goal is to make it nearly linear time. That is exactly what we did. So for any epsilon going arbitrarily close to capacity, there is a nearly linear time algorithm for doing this job, this univariate multiplicity code decoding. And a couple of caveats which are reasonable: constant rate and the field to be of larger characteristic. This is so that the interpolation goes through properly. So okay, let's let me look at the moment. How do we go about this? If you recall the two steps, the interpolation step followed by the differential equation step, we need to speed up both this time. So the step 1 speed up is pretty much identical to Alekna, which is interpolation speed up of Guruswami-Wang. So construct a lattice and find the short perspective. Basically verbatim Alekna, which is algorithm. The step 2 speed up, this is now more interesting because now you need a fast solver of differential equations of this form. Okay, that equals 0 wasn't supposed to be perfect. Basically, the unknown polynomials are put in this other color. These are the ones that you know already from the first step. So, how do we solve differential equations of this form? Fast, nearly linear. So, just repeating the equation here. So, since it has a sort of affine structure, so degree D solutions form an affine subspace, and we want to find a basis for this. Now let's look at a simple case. If it was just A naught x plus A1x Rx, how do you solve this differential equation? It's barely a differential equation. How do you solve it? Well, you just take A naught to the other side and divide it. So by long division, you can solve it, and it has a unique solution. But how about, can you do this in linear time? Actually, yes, you can do long division in nearly linear time, but I want to introduce a method that can be easily generalized from this to higher n. So how are we going to do it? So what we're going to do is write R of x as two parts, a sort of a low degree and a high degree part. So we're going to write it as ux plus x to the d by 2 vx. U and v are still unknown because R is unknown. And if you remember, we had A naught plus A1 R equals 0. If you substitute this R is equal to U plus x to the d by 2 v, you have this. Now this is, we want this to be exactly equal to 0. If it's equal to 0, certainly it's equal to 0 mod x to the d. If you can smell a divide and conquer on the horizon, you're right. There's a divide and conquer. It's about that. So what we need is, so there's a low degree part to the left and a high degree part to the right. So we need this part, A naught plus A1 U equal to 0 mod x to the d. And the second part, if we call A0 plus A1 U as B, then we need B plus x to the d by 2 A1 B equals 0 mod x to the d. Can we divide and conquer yet? Not yet, because the second one isn't a smaller instance. So it is written the same thing over here. However, from the first line, you can see that B is supposed to be divisible by x to the d. So everything over here has an x to the d by 2. Right? So we can take it out. So then, yeah, so if you write, if you call b by x to the d by 2 as c, now you get, just rewriting the second one, you get c plus a1b equals 0 mod x. So, yeah, the sharper right among you would notice that c is not on, it still has a u inside it. But once you solve the first one, you can get to the second one. Essentially, you have now two smaller problems of the same type. You can reverse and stitch them together at a point. So this is not quite what we do, because for higher m, the solutions are no longer unique, and we can't afford to branch or take cases because we want to do this in nearly. We don't have the time to do it. So what we do is go back and forth with Guruswami-Wang and Kopparty. We essentially construct a proxy differential equation, and we make a version of a divide and conquer work over there. So that is how we speed up the second step, the differential equations step. So a few remarks and open questions. So everything that I just said also works for folded Reed-Solomon codes. The other variant of Reed-Solomon that also attains it. So we basically have near linear time decoding algorithms for both variants of Reed-Solomon that can be decoded at different times. Something we don't know yet, can we generalize this to multivariate polynomials? And for just Reed-Solomon codes, some of you might have heard of a recent result that generic Reed-Solomon codes achieve this decoding capacity. That essentially means random evaluation sets, but we don't know specific evaluation sets for which this is true, and we also don't know algorithms for what those sets might be. So lots of things still yet to be done in the Reed-Solomon going up the capacity world. But this is what we have done. We done near time this decoding of univariate multiplicity codes. And the main big thing we had to do is via fast differential equations. So that's what I have to say.
I mean, does this work in a more general setting?
So it's just I mean, it solves the equations of that type. I don't know anywhere else where those specific things arise, but might be available. Any questions? Okay, let's thank the speaker.